and we end up with a second derivative of 1.25708. Let's make that negative because we do have this negative here, times the sine of 0.524 t plus 1.377 times this derivative would be 0.524. Now what I'm wanting to do with this is, all I want to know is what's the sine. So we're going to determine the sine of the second derivative at the zeros of the first derivative. So our zeros of the first derivative were about 4/10 and about 6.4. So if I look at the second derivative and I put in my approximate 4/10, is there anything in this that's going to make it negative? I've got a positive. Well, let's go back. We have to kind of look at this. I'm going to write this so I can see it easier, and hopefully you can too. We had this negative. We pulled it out in front. So this is going to be a negative times a positive, and sine is going to be, well, we need to determine, is sine positive or negative at that point? We're going to have to evaluate that, and we can use our inspires to do that. I'm going to come back with you in just a second, and I'll verify my notes, but at the same time, you can pause this and you can put this quantity in and find out if I put 4/10 in here, is it going to be positive, this whole statement positive or negative? Okay, let me show you what I was doing to get ready to evaluate what we're working on here, and this will give you some hints as to how you might want to work this when you come down to the final quiz that we have on finals day. What I did was to define f1 of x to be our function, take its derivative, define f2 of x to be that derivative, and then take the derivative of that, and then define f3 to be the derivative of f sub 2. So f1 of x is the function, f2 of x is the derivative of the function, and then f3 of x is the second derivative of the function. So if I'm going to now evaluate, as I want to here, what is the sine of 4/10 into the second derivative, I'm going to type f3 of 0.4, and that is negative, so I just need to come over here and say that is negative. The conclusion is that at t equaling 0.4, r of t is if it's less than, is a maximum. Okay, because we're concave. If it's less than, then we're concave down, which makes that a maximum. So let's try the next one, and we'll take f3 of value is 6.4, and at 6.4 we get positive. We get positive 0.65. And so at that point, the second derivative at 6.4 is positive. Our conclusion is that at t equaling 6.4, r of t is, it's positive, so it's opening up, so this would be a minimum. Let's go back up and check. It says determine the extrema. So we have the extremas occurring, t being 0.4 and t being 6.4. Now let's go back and put this in relevance to the problem. We're talking about monthly rainfall at the Seattle-Tacoma Airport. T being 1 is January. We find that when T is 4/10, we actually have a minimum. Well, when is T equaling 4/10? In a year. If T is 1, this is a little interesting here. If T is 1, then we are talking about January. So exactly when is 4/10? And you could argue that it's in December, although we would probably think that 12 would be then December. 4/10, I think I'm going to go with sometime in January. So the month of January is going to give us our maximum rainfall. And so when does that make 6.4? Well, if we think about January being the first month, then June is the second month, and so, or the sixth month, and so it's 6.4, which again, it's a little difficult, you know, 4/10. If 6.4 is June, then wouldn't 1.4 be January? So is this December, January? I'm gonna let that discussion be your decision there, but we know that it is cyclic, and we do know now that we have a maximum and a minimum, and it's in the December-January time frame and in the June-July time frame. Okay, so that finishes then the first part of the problem, which is to determine the extrema. Let's go to the next one, which is says integrate